that's fine.
Okay, great. And I see we're live now. Okay, so let's admit. Okay, so I'm very happy to introduce our next speaker, the first for the afternoon. Our next speaker is Guy Bresler from MIT, and he's going to talk to us about reproducibility and statistical computational gaps from secret leakage.
Great, thanks very much. It's great to be here, and thanks for the invitation, and for all of you for tuning in. So this talk is about the computational complexity of statistical estimation problems. In the broader research community, these problems have largely been studied in isolation, and the central theme of this talk is that there is a lot to be gained by instead focusing on the relationships between problems. So this is joint work with Matt Brennan, PhD student at MIT, and the archive link to the paper, which contains everything that I will be talking about, is here at the bottom of the screen, and this also appeared at the latest conference on learning theory. Okay, so each of you has your favorite statistical estimation or statistical inference problem. Typically these days, these are high dimensional problems. So there's often a parameter D for dimension. There's some structure, for example, sparsity, and there's a parameter indicating what that might be. You have data, so number of samples N, and there's some signal strength parameter or SNR parameter theta. And at the highest level, all of these problems are basically to estimate some signal in random noise. So the basic question in mathematical statistics and information theory and related areas is, well, how much data do I need in order to solve the problem of interest, right? And you care about this both as a practitioner and as a theoretician. To get a sense for how a typical problem behaves, we'll look at sparse PCA. Probably many of you have seen this problem, but if not, it doesn't matter. It's just to illustrate. And so this problem does indeed have these parameters, and we're going to plot a sort of feasibility diagram where on the vertical axis here is theta, the signal strength, and it's going to be parameterized as n to the minus beta. So as we go up, the signal gets weaker. And on the horizontal axis, we have the sparsity k, the number of non-zeros in the planted signal. So this problem has been widely studied over the last couple of decades, and the question of how much data do I need was, for all intents and purposes, solved by Berthet and Rigolet in 2013, where they found the following phase transition between possible and impossible. And it occurs at a signal to noise ratio or signal strength parameter theta that looks as what's given here, root of k log d over n. Now, you would think that this would be the end of the story, but they were also interested in efficient algorithms, and they observed that efficient algorithms seemed to require more data, square root of k squared over n. So there's an extra factor of k in there. They were very disturbed by this, and they wanted to understand if it's fundamental, and they showed that this triangle here in red is actually computationally hard in a certain sense that will be understood as the talk goes on, which indicates that in general, you can't hope to improve this green triangle, at least in terms of like where that line lies, the line. Okay, now subsequently, there's multiple questions here. One is to find more algorithms, the other is to fill in those blank regions of the diagram. And there are a huge variety of algorithms, each with their own advantages. And the blank regions of the diagram were closed in the last couple of years in joint work with Matt Brennan and also with Wasim Halehel in two separate papers. So maybe one thing that you might notice is that while this is nice to have fully settled the feasibility diagram for sparse PCA under the spectral covariance model as it's known, this is a lot of papers indicating a huge amount of work by a lot of people to arrive at this sort of story that describes what's happening. Now, sparse PCA is just one amongst a huge zoo of problems. There are, for instance, graph matching problems, graph clustering problems, a variety of problems from signal processing, cryo-EM, various tensor problems, tensor completion, tensor PCA, et cetera, et cetera, et cetera. There's a gazillion of such problems. And you might wonder whether we have to go through this large amount of work for each of these problems individually to understand the limits of what computationally efficient algorithms can achieve for each of these problems. So in order to get a sense of kind of how these problems behave, it'll be useful to look in a little more detail at a specific problem. It's arguably the simplest problem from this kind of general class of problems, and that's what's known as the planted clique problem. So the planted clique problem, maybe some of you have seen this before. It's a simple graph, sort of cluster graph inference problem. So there is a random graph, an Erdős-Rényi random graph, where each edge is present independently with some probability. It could be half or a quarter or whatever. And then there is a k-clique, so a fully connected subgraph on k vertices that's placed uniformly at random in the graph. Now, of course, you don't know the identities of the vertices when you're trying to determine where this k-clique is. And of course, they're also, the edges are not in red. And that's the planted clique problem, is find the clique that's been placed in the random graph. So it's going to be convenient to have a picture, which is just the adjacency matrix of the graph. And so here, I'm going to define the hypothesis testing variant of this problem, where the task is just to determine, is there a clique planted at all, or is it just a purely random graph? And so here we would have the null hypothesis for planted clique is that the entries of the adjacency matrix, well, it's symmetric, but in the upper triangle are Bernoulli half. And the alternative hypothesis is that there is a submatrix of all ones. It doesn't necessarily have to be contiguous like this. It's just a over some subset of S columns and rows, there are ones planted. Okay, so this is a hypothesis testing problem. Turns out to be equivalent, actually, in a strong sense, to the estimation problem of finding the clique. And for the purposes of this talk, we'll just consider hypothesis testing problems. Most of what I'm going to say applies also for estimation problems, but it's just going to be simpler to think about hypothesis testing problems. Okay, so what's known about planted clique? Well, here there's just one parameter, k, for any given graph size n. And so we'd want to know, well, how big does k have to be so that we can solve the problem? And if k is bigger than roughly 2 log n, then the size of the clique that's been placed in there is bigger than the largest naturally occurring clique in an Erdős-Rényi random graph. And so one can detect it, the presence of the clique, by searching over all size k subsets. Well, that's clearly inefficient. What about efficient algorithms, polynomial time, let's say? Well, if k is bigger than a constant times root n, then it is known via a variety of algorithms how to detect or find the clique. But this is exponentially bigger than the log n threshold that's the information theoretic or feasible in principle threshold. So despite lots of work over the last few decades, square root n has not been improved upon, and it's widely believed to be computationally hard to find the clique or to detect its presence when k, the size of the clique, is smaller than root n. And there is a variety of work giving evidence of various forms that this is the case. So just one word regarding terminology. I'm often asked, what is average case? I use the word average case here and there. This means that the input to the problem of interest is drawn from a distribution. Planted clique you could think of as an average case version of max clique, which is the classical NP-hard problem. All right, so the planted clique conjecture, which is just a reformulation of what I said, this belief that it's hard to detect the clique when k is smaller than root n, is conveniently depicted in this diagram here at the bottom. And this is a one-dimensional phase diagram, which says that the problem seems to be hard, or is conjectured to be hard, up until this half. But the parameterization here is that k is n to the alpha, so this would be the root n. And so above this threshold, the problem becomes easy. The clique is so big that it can be found in polynomial time. So this is the planted clique phase diagram. It'll appear again. Now, like I said a moment ago, there are many, many, many such problems, and many of them, in fact, pretty much all of them, these structured inference problems, seem to have a computational statistical gap where the amount of data or the size of the signal that is needed in order to efficiently solve the problem is much higher than what is needed in principle, information theoretically, if one is not computationally limited. And so both from the philosophical and the practical side, it's crucial to understand how much information can a computationally bounded observer infer about the world. And this is in stark contrast to the central way of studying these problems in mathematical statistics for the last 120 years, which is just about how much data do I need, not how much data do I need for an efficient algorithm to solve the problem. All right, so the broad objectives of this general research program is, one, how much data do we need? What's the computational data limit? And we'd like to give evidence for it. So if a problem is believed to be computationally hard for some parameter regimes, one would like to show that in some convincing way, because then you could conclude that certain algorithms are indeed optimal, and you'd like to, of course, find what those algorithms are. At some more vague philosophical level, we'd like to understand the basic phenomena of like what's going on here. Why are computational limits leading to a particular threshold for the amount of data that's needed? And finally, if we're to be really ambitious and to dream a bit, we might hope to understand relationships between these problems to try to understand, are these phenomena really the same? If we understand one problem, does that lead to an understanding of another? If we have algorithms for one problem, does that give us algorithms for another problem? And so forth. So the goal of this talk, given these broad objectives, is to address them to a degree for a collection of problems. We're first going to motivate and explain the average case reductions approach, which is relating these sorts of average case statistical problems directly one to another. Then we're going to use the average case reductions approach to get a unified understanding of the computational phase transitions and feasibility pictures for a variety of problems with different structures via a generalization of planted clique that we just discussed a few minutes ago. In particular, we're going to illuminate a small piece of this web of reductions, this diagram, which is what's carried out in the paper that I linked to in the beginning. And here at the root is secret leakage, the typo, secret leakage planted clique, the generalization of planted clique that we use to connect all of these problems one to another. All right. So like I said, we're going to start with a little background on average case reductions, and then we'll go into the techniques and some of the results in a little while. Okay, so background. So I should say one thing, which is, I don't know what percentage of the people who are listening to this have access to ask questions and interrupt me, but if you do, then please feel free to interrupt me and ask a question if something's not clear. I'm happy to take a moment and answer any questions. Okie dokie. So some background on average case reductions for statistics problems. So yeah, so we're interested in complexity of statistics problems. And if we look at the field of computational complexity, whose business it is to understand the computational complexity of a variety of problems, there is an amazing amount of understanding that's been achieved by classifying different problems into equivalence classes and finding relationships between these classes of problems. And so you can go surf the complexity zoo and look at relationships between various classes of problems. And the basic way that one reasons about the computational complexity of one class versus another, or one problem and how it relates to a given class that contains it and so forth, is via reductions. So reductions, what is that? They were popularized and really kind of brought to center stage by Karp's famous paper, Reducibility Among Combinatorial Problems. So what's the basic idea? The basic idea is that one starts with some problem, for instance, 3-sat, and one takes an instance of 3-sat and transforms it, for example, into an instance of independent set in a graph. So one constructs a graph and an independent set corresponding to solvability of the specific formula that's being given. And this mapping should be done in polynomial time, so that one could then use an algorithm that solves independent set to solve satisfiability. That's the basic idea of reduction. You're transforming one problem into another. A little more specifically, how is this done? The specific reduction, it's done by producing a gadget for each clause in the formula. This gadget has some specific structure that's illustrated here. And what one sees immediately is if one cares about average case versions of these problems, where, for instance, you might have some uniform distribution or some nice distribution over satisfiability formulas. You might have some nice distribution over graphs in which you would like to find independent sets. The transformation via these gadgets clearly just destroys any natural probability distribution. You end up with these little gadgets stuck everywhere, and this doesn't correspond to any reasonable probability distribution. So the takeaway is that the traditional way of doing reductions for worst case problems just doesn't work for average case reductions, where one has to preserve the probability distribution over instances. Nevertheless, the dream that we like to advocate is maybe nevertheless one can still carry out such a program of doing average case reductions between statistics problems in order to elucidate this landscape of problems and relationships between them. So I'm going to next spend a couple minutes describing an appropriate notion of reduction, which targets specifically obtaining the correct distribution. And this is a notion of sort of statistical reduction, or reduction for statistical problems. So just a little bit of notation. So we're going to write, instead of the total variation between a distribution P and a distribution Q being less than epsilon, we'll just write P is approximately sub epsilon Q. And some even more important notation here. It's just mostly going to be in the next couple of slides, but it's just, this won't make sense without this notation. So if X is distributed like P, and you have some random algorithm, randomized algorithm A, that takes X and then it arrives at something that's close in distribution to Q with an epsilon in total variation, we'll use the notation P is mapped to Q under A. So A sits there on top of the arrow within error epsilon, so sub epsilon. Okay, so A takes an instance drawn from distribution P, and the output distribution is Q up to error epsilon. One small fact is that by the data processing inequality for total variation distance, it's a general property of F divergences, you can compose these relationships and the errors add up. So if P maps to Q with error epsilon 1 and Q maps to R with epsilon 2 error by an algorithm A2, then the composition of these algorithm maps from P to R, and the error is just at most the sum of these two errors. Okay, so now the notion of reduction that we want is we would like to start with some hypothesis testing P. So there's a distribution that's the null hypothesis. You're observing something from that null hypothesis. Alternatively, there's the distribution P sub H1. You don't know which of these two is true, but we would like an algorithm that takes an instance of whichever of them is true and maps them to a different hypothesis testing problem, P prime sub H0 or P prime sub H1, and it's correctly mapping the null hypothesis of P to P prime, and similarly for the alternative hypothesis, like I said, without having any clue of which of them is reality, which of them is the case. Why is this the right notion of reduction? So there's also, I should say, a little of 1 here, which just means that the total variation distance is vanishing asymptotically as the problem scales. So why is this the right notion of reduction? Well, if somebody came to you and said, hey, I can solve the P prime hypothesis testing problem. So this would be algorithm A prime here. Then you'd say, oh, this is great, because I actually care about the P problem, not the P prime one. But if I want to solve the P problem, I can apply algorithm A, get an instance of the P prime problem, so that if, for example, H1 was the true hypothesis in the problem that I care about, the problem that I have to solve, A would then map to alternative hypothesis H1 for P prime. And then, well, you genuinely have an instance of P prime, at least up to total variation distance that's vanishing. And so the A prime algorithm would solve it, and you would then have a solution to the original problem. And so this sort of notion of reduction transfers the challenge of solving one problem into the challenge of solving some other problem. And that's precisely what reduction means. Okay, now an important note, of course, is that if A prime runs in polynomial time and the reduction itself runs in polynomial time, then the composition of these two algorithms also runs in polynomial time. And so if one has that A prime is a polynomial time algorithm, then one obtains a polynomial time algorithm for the original problem. And so this is a useful algorithmic transfer. Conversely, if the original problem was indeed hard, this would rule out the existence of a polynomial time algorithm A prime for the P prime problem. Okay, so hopefully this makes sense. This is a little bit more delicate of a notion of reduction than the worst case one. Okay, so just an example of what this sort of reduction looks like, transfer of what the connection between two problems looks like in an actual statistical problem. So one might have plenty clique here on the left. The null hypothesis just has Bernoulli halves in the entries. The alternative hypothesis has the clique there, and so then there's the block of ones. The paper of Ma and Wu in 2014 studied the biclustering problem, which looks a lot like plenty clique. In the null hypothesis, there's a Gaussian matrix, so standard Gaussians independent in every entry. And in the alternative hypothesis, there is a submatrix which has elevated mean lambda. Okay, so the notion of reduction that would allow one to conclude things about biclustering here is the one that we talked about, and you'd want to be mapping the corresponding null hypothesis to the null hypothesis of biclustering, and similarly for the alternative hypothesis. All right, why is that good? Well, if one starts with an instance of plenty clique that's hard, one could then deduce hardness for an instance of biclustering. For instance, you would like to deduce hardness for the hard labeled instances in this biclustering feasibility diagram, which is labeling any given parameterization, any given parameter value instance for biclustering as easy, so they're just polynomial time, or impossible with information theoretically hopeless, or just computationally hard or infeasible in principle. And so to conclude that it's hard, the whole way of arguing that it's hard would be to map from a hard instance of plenty clique in this manner that I just described. Okay, so back to our broad objectives. We see how reductions allow us to achieve those at the high level. I should say, however, that there are a number of other approaches in the literature and the actively researched by the community that are aiming to do at least the first two of these, to predict the computational data limit and to find optimal algorithms. And the primary of their approach is to analyze the performance of restricted classes of algorithms. So one takes some powerful class of algorithms, for example, the sum of squares hierarchy. And if you want to reason that a certain region of the feasibility diagram is hard, well, one would show that this is hard for those sum of squares algorithms. Okay, so clearly this is in some ways powerful because it's just saying that this class of algorithms simply cannot solve this problem in this range of signal to noise ratios, for example. But the primary weakness is, one, that this has to be carried out separately for every problem that you wish to study. And there are many classes of algorithms, many problems. This is going to be a lot of work. And second, it's not future-proof. If somebody next week comes with a more powerful class of algorithms, then one has to repeat the work of analyzing the performance of that new class for every already studied problem. And so that's maybe not entirely satisfactory. So average case reductions subsume hardness for restricted models of computation. If we care about, for example, polynomial time computation, and the source problem, for example, plenty clique, has been understood and its sum of squares hardness, for example, well, then average case reductions would transfer hardness for polynomial time algorithms from the root problem. And so it's a stronger way of reasoning about computational hardness. More philosophically, average case reductions explain how a phenomenon in one problem arises due to the same phenomenon in a different problem, because, well, there's the original problem that you're mapping from is kind of living inside the one that you've mapped to. And so it's really quite a deep insight into the problem that one reduces to. And finally, it simplifies the landscape. I mean, in some dream world, you could imagine that some huge collection of problems were shown to be fully equivalent, and then one could understand any one of these. For us, because the situation is directed tree away from the source problem, it'll just suffice to understand the hardness of the source problem, which for us is secret leakage planted clique. So for these reasons, reductions are the gold standard, but their scope has been pretty limited for statistical problems, which is the reason that analyzing restricted classes of algorithms is so popular, that reductions seem to be very challenging and limited in scope. One particular complaint about results that use reduction so far is that many of them start with planted clique and then map to some statistical problem that looks more or less like planted clique. It has some submatrix signal that's sparse, there's some independent noise. And so aesthetically, it's nice to be changing the distribution and nice to be changing details of the problem, but fundamentally the structure of the signal is the same as that of planted clique. And there are many, many, many problems that don't have this structure. And so if the reductions approach is to have any real hope of explaining this landscape of problems, the first obstacle is to ask ourselves, can we get out of this sparse submatrix signal plus independent noise situation, this class of problems? So that's the main question. Our answer is yes, indeed, one can depart significantly from sparse submatrix plus noise, but planted clique does not seem like the right starting point, while it has been the starting point for the vast majority of existing reductions in this field. And so instead of planted clique, we consider secret leakage planted clique, appropriate generalization, and together with that, we introduce a number of new average case reduction techniques for transforming distributions. And so I'll describe in the remainder of the talk a couple of these techniques. There are a slew of other techniques in the paper, and it's really, it wouldn't be possible to explain what they are, but I'll focus on a couple and hopefully give a flavor of how these sorts of reductions are carried out. Okay, so again, here's this this diagram. We're gonna briefly, before I talk about the techniques, in just a few minutes, I'm just gonna say a few words on what exactly is secret leakage planted clique, and then we'll go to the techniques. Okay, so secret leakage planted clique. So remember planted clique, you start with an Erdős-Rényi random graph, and then you place a clique uniformly at random. It's conjectured to be hard if the clique that is placed is smaller than square root of n in size. Turns out that it's very convenient for us to consider some slight modifications of the standard planted clique problem. So for example, we consider a k-partite version of planted clique. And so here there are k different groups of vertices, and the clique is guaranteed to have one node from each of these groups of vertices. Okay, so we haven't significantly changed the problem because for all intents and purposes, the number of possible clique positions is almost the same as it was originally. We've just slightly constrained the position. And indeed, we conjecture that this problem is still hard at the same threshold as planted clique. But we have introduced a little bit of structure that's not there in the original planted clique problem. Okay, so there are several other such variants of planted clique, bipartite planted clique, k-part bipartite planted clique, and a k-partite hypergraph version of planted clique. So each of these are useful for different sets of reductions. And instead of just carrying around all of these, one could just assume each of these is hard on its own. It's conceptually useful to abstract away what's happening here and just think of all of them as an instance of a more general problem that we call secret leakage planted clique. So what is secret leakage PC planted clique? We just have some distribution rho that's not necessarily uniform over the possible positions of the clique. The clique is sampled according to rho, and that's placed in an Erdős-Rényi random graph. So just like planted clique, it's just that now the clique position isn't uniform at random. All right. You could think of this, and this is where the name secret leakage comes from, by the way, as having a little bit of information about the position of the clique. So your sort of prior is no longer uniform. All right, so the four examples that I wrote on the previous slide, they're all instances of this with a certain prior. And well, when is this problem hard? It's not always hard, and you can convince yourself that because, well, if rho is just delta function on vertices 1 through k are in the clique, then the problem is very, very easy. You can just look at those vertices and that's it. You'd find the clique deterministically. So it clearly depends on rho. And there's a clean conjecture that we have for when this problem is actually hard. And I'll state it as follows. So let S and S prime be two independent draws of the clique position from distribution rho. Consider the probability mass function of the cardinality of the intersection of S and S prime. So this is the overlap between two independent cliques. And if it decays at a certain rate, this probability mass function, then the conjecture is that there is no polynomial time algorithm. And so this is a clean conjecture that includes the special cases for the various specific instances that I mentioned before. All right, now, why should we believe this conjecture? Well, it's supported by a heuristic that's called the low degree likelihood ratio. It's sort of a proxy for sum of squares algorithms, as well as the statistical query framework for arguing about computational hardness. But outside of these, if somebody wants to go find some better evidence for hardness to see whether this conjecture is true or not, we very much invite people to do that. We would love to have evidence accumulated for this problem. And somehow the whole point of the reductions approach is that the evidence that's obtained for the threshold for secret leakage is then automatically, in some sense, transferred to all of the rest of these problems in this web of reductions. All right, so in the remaining time, 12 minutes or so, I'll give a sense of a couple of different reduction techniques. One of them is very simple and is basically a change of measure. The other one builds on the change of measure to change the structure in a meaningful way. Okay, so the motivation for the first technique and the technique itself is from, or at least in part, from this paper of Ma and Wu that I said before, where they study biclustering. And so here one wants to understand for which values of n, the size of the matrix, k, the size of the planted matrix, lambda, the size of the mean in the planted matrix, is it feasible or infeasible to detect the presence of this elevated mean submatrix? And so in this feasibility diagram, we have the x-axis is parameterized by alpha. That's the polynomial size of k in n. And then the vertical axis is lambda, the signal strength, and it's getting weaker and weaker as we go up because beta is growing. So now, in order to carry out a reduction, one wants to start at planted clique and map to biclustering. This is just a natural choice for a starting point, planted clique, because, well, these problems look quite similar, and that's what they did. And so now, the simplest possible thing that you could imagine doing is just taking the adjacency matrix of planted clique, and let's forget for a moment that it's symmetric. There is another trick that one can use to deal with the symmetry. And one might want to map an entry from the planted clique adjacency matrix, which is either going to be Bernoulli half or Bernoulli 1, just a 1, to the corresponding entry in the biclustering problem, the Gaussian problem. So those entries are either going to be standard Gaussian or normal lambda 1. So what we want is a random mapping, which if the input is 1, well, then you might be from the planted clique, and so you had better map it to normal lambda 1. And so we want on input 1 to produce a sample from this appropriately elevated mean Gaussian. And if the input is Bernoulli half, then you want to output something from the standard Gaussian. And one can solve a system of 2 by 2 linear equations to obtain that if the input is 0, one would like to produce a sample that has distribution to phi 0 minus phi 1. Sorry, this should be 2 phi 0 minus phi lambda, where phi 0 and phi lambda are the densities of the appropriate Gaussian. And you can check that indeed Bernoulli half will then map to the half-half mixture of phi 1 in case you got a 1, and this 2 phi 0 minus phi lambda, and the phi 1s will cancel, and you'll be left with the appropriate thing, which is phi 0. So this is the idea. Now, there is a big problem. The big problem is that it's impossible to just produce a sample from 2 phi 0 minus phi 1 or 2 phi 0 minus phi lambda. The reason is that this isn't necessarily a density. If we plot it, it's the purple curve here and it goes negative. You can't have a negative value for a density, for a probability density. Luckily, it turns out not to be a huge deal. And what Ma and Wu do in their papers, they essentially condition on not landing in the region of negative density. So they're kind of truncating this density. And if the truncation happens at the appropriate place, one can argue that there is not a huge loss in total variation distance. And so the mapping does what one wants up to a small error in total variation distance, and therefore accomplishes the requirements of a reduction. I should just briefly mention, we require a generalization of this that takes an arbitrarily distributed Bernoulli random variable and outputs two distributions f and g, depending on whether the input was Bernoulli p or Bernoulli q. And there's an efficient procedure that we developed to produce these samples without knowing which of the two is true, Bernoulli p or Bernoulli q. And the basic idea is to use rejection sampling in kind of a slick way, but I won't go into the details here. Just to mention that one can generalize the mapping from Bernoulli to Gaussian significantly. Okay, so this is a cosmetic change, this change of measure, change of distribution. Turns out it's also useful for changing the structure of the planted signal. And that's what I'm gonna talk about for the remainder of this talk, is a technique that we call Bernoulli rotations. And so it's a change in the planted structure of the signal. Now, the context is gonna be that we have an input, which is a vector of i.i.d. Bernoulli half, random variables, and there is some single position I that's been fixed to 1. Okay, and the fact that it's a vector is just for convenience, where you can think of it as a flattening of a matrix in some situations, or flattening of a tensor in other situations, or just a vector. But this is a sort of sufficiently general. Now, what we're going to output is a Gaussian vector with independent entries, and the mean vector is a sub I, where a1 all the way to an are a given collection of possible mean vectors. So ai is going to be the output if the input had its ith position fixed to 1. Okay, now formally, planted Bernoulli with ith coordinate planted to 1 gets mapped to Gaussian with mean vector ai, identity covariance. Tau here is some small scaling, causing a logarithmic loss. There is this lambda here, which is the maximum singular value of the matrix A that's formed by stacking these rows, which does end up playing a pretty significant role from the technical side of things, but we won't get into that. Okay, so the planted vector with an ith coordinate being planted 1 gets mapped to the Gaussian with mean vector ai, and if everything is just Bernoulli half, so there is no planted 1, then the mean vector is just all zeros. So this is the output of Bernoulli rotations. What's the actual algorithm? I'll say in a second. I guess it goes without saying that this is somehow very generic. In the applications, it's crucial to choose these mean vectors AI in a very sort of careful way. Okay, so here's the Bernoulli rotation algorithm. It's going to accomplish the guarantee of carrying out this mapping from the previous slide. So here's our input. It's our the vector of zeros and ones. It's a sample from the planted Bernoulli vector. We're going to apply the Gaussian rejection kernel, which Gaussianizes each entry to produce a vector v prime. We're going to sample some other vector u, which is isotropic Gaussian, and then we output this vector x, which is matrix A times v prime. So it's a linear transformation applied to the Gaussian vector. Of course, we don't actually know the mean vector for v prime, right? Because depending on which planted vector was one, v prime will have a different mean vector, but that's fine. We don't need to know its distribution. I mean, we have some specific set of numbers and we can apply this linear transformation to it. And then the second term here is introduced in order to cancel the induced correlations that are created via the linear transformation A. And so eventually, once one carries out the analysis of what this mapping is doing and computes covariances and means and stuff, one concludes that X has the distribution, which is has the correct mean and covariance. All right, so in the final few minutes, I'm going to give a sense of how to use this Bernoulli rotations algorithm along with the choice of AI to actually say something concrete. A lot of kind of general things have been said, and this is in the context of sparse mean estimation. So sparse mean estimation is the following hypothesis tested problem. Either you have isotropic Gaussians, so n samples from isotropic Gaussian in d dimension, or there is some sparse, k-sparse planted mean mu. This is sparse mean estimation. Just detect whether there's a sparse mean there. This problem does not have a computational statistical gap. The information theoretic limit is efficiently achievable. However, if one considers robust sparse mean estimation, where some epsilon fraction of the samples is allowed to be contaminated, so this is known as Huber's contamination model, then it turns out that there is in fact a computational statistical gap. So suddenly, efficient algorithms seem to no longer be able to achieve the information theoretic limit and require an extra factor of k there in the number of samples. And this has been showed within the statistical query framework by Diaconicoulas, Kane, and Stewart. Okay, so how can we map to robust sparse mean estimation from planted clique or from secret leakage planted clique? Well, it's going to be useful to look at essentially at the high level, how does a cartoon version of robust sparse mean estimation even look? So this matrix in the bottom right is just the mean matrix. So we have in the d dimensions, which are the different rows, there's k non-zeros there because the means are k-sparse. And then one can imagine having a specific contamination model, a specific adversary in Huber's contamination model, which just puts some other mean in a subset epsilon of the samples. And so these are these red ones. They have some crazy mean mu prime, which isn't the original model specification. And then the remaining ones have the mean mu prime. This is a cartoon of how this problem looks, and it'll guide us in mapping to it. Okay, so the plan is as follows. One starts with a k-part bipartite instance of planted clique, which looks like this. There are these partitions of the vertices on each side, which result in these blocks. There's a single one there, which corresponds to the clique vertex. We apply Bernoulli rotations to get a Gaussian vector with some mean. That mean corresponds to where exactly the one that's planted is located. And so now we've replaced each of these planted vectors in these blocks by the corresponding Gaussian with the correct mean. So one now has this Gaussian matrix, and the question is, well, how do we choose these vectors for the means, the A's? In other words, how do we choose this A matrix? It turns out that a somewhat delicate construction is needed in order to achieve the right thing, and that's largely because of the sigma max is bounded, the singular value is bounded, and so this matrix needs to be roughly orthogonal. It needs to have two values because the robust sparse mean estimation problem had two values there, and a certain proportion of them need to be positive and a certain proportion of them need to be negative and so forth. And these requirements are met by a matrix constructed from the incidence geometry of hyperplanes and points in the appropriate vector space over a finite field, FR to the T. And so that construction, I won't have time to explain sort of why it works, but just the the various combinatorial properties of these incidences turn out to exactly correspond to give the correct output, leading to an instance of robust sparse mean estimation. This is one example reduction technique, is this Bernoulli rotations. It's used in various of the other reductions in these arrows, along with a bunch of other reduction techniques that are each justified via their own set of probabilistic arguments. So the set of problems that we map to, that we get reductions that give tight computational statistical trade-offs in this paper are the ones listed here. And I'll briefly conclude. So the sort of primary starting insight for this paper is maybe we shouldn't be starting with planet clique anymore. We should start with secret leakage planet clique, a generalization of planet clique, which then gives us power to map to many different problems with very different structures than planet clique. The reductions are justified and motivated by a variety of different reduction techniques, and we're optimistic about this direction in general and quite excited by it. There's a whole lot left to do, so we invite further activity by others in the community in this area. So thanks very much.
Okay, thanks for the really fascinating talk. Are there any questions from the audience? You can either raise your hand or you can type a question into the chat box.
I have one question, if I may ask. I was interested in this remark that you made. So does it make any sense to consider reduction to problems where there is no computationally hard gap? So what basically like happens in this case? So to the variant of the problem. And to be more concrete, also on one of the very first slides, so you mentioned graphical model learning as one of the class of problems. Is there so this is like one example where normally there is no computationally hard gap. So what is known about that, and is there any
perfect
reduction?
Yeah, I'm happy to say something first about the second question, and maybe then I'll say something about the first. So yeah, thanks for the question. So in certain graphical model learning problems there is no gap. In others there very much appears to be a gap. Just as one small example, you could consider the spiked covariance model for sparse PCA, and that would correspond to detection or recovery of a clique graph in a Gaussian graphical model. So just an empty graph and with a k-clique there is what the Gaussian graphical model corresponding to the spiked covariance model is. And so for that problem, there would of course be a gap because it's just sparse PCA, and you could just phrase it as a graphical model estimation question. So beyond that, there's not a whole lot that I know how to say, just that there does appear to be some interplay between the sorts of structures that you're trying to estimate in graphical models and whether there is or isn't a gap and where exactly that gap is. And there is a paper of Han Liu and co-authors where they have some maybe first step in this direction to try to understand combinatorial criteria of graphical models. But I think there's a rich area and there's a lot left to do in that direction. About the first question, would it make sense to map to a problem that doesn't have a gap? I think absolutely yes, if your focus is on algorithms. And so one basic way to view a certain style of reduction is just use of one algorithm as a subroutine for another. So if you want to solve some problem and you use some other problem as a subroutine. So for example, sparse linear regression can be used as a subroutine to solve various other problems, including sparse PCA. And so that's really just a reduction. One's reducing sparse PCA to sparse linear regression in a certain regime of parameters, and it gives you an algorithmic result. However, of course, if you're mapping it to a problem that has no statistical computational gap, then there's nothing to be reasoned about regarding computational hardness. So it depends on your objective.
Great, thanks.
Thank you.
Okay, any more questions from the audience? Okay, and in that case, we will we'll thank Guy for the talk again, and we'll move to the breakout room where we can have further discussions.
Great, thanks everybody.